Welcome to our first part of a three-part series of lectures where we'll be talking about using molecular modeling in the context of Chem 344 to support some experimental observations and results throughout the semester. We're going to talk in three parts about how to think about the concepts of molecular modeling, specifically today molecular orbital theory, hybridization, formal charge. We're going to think about these chemical concepts and how they relate to reactivity. And then in the second part, we're going to take a look at how to actually use the software to perform the calculations yourself. And in the third part, we'll take a look at different applications of these calculations in terms of chemical reactivity and try to think about how we're going to use these calculations in the context of this course. The software we're going to be using throughout is used to produce these images here called WebMO, which is a front-end software that works as a really nice user interface to allow you to perform calculations using Gaussian 09, which is a higher-end computational software that's installed on our computer cluster on the 9th floor in the chemistry building. The software that we're using, WebMO, is developed by a professor at Hope College, Professor Pollack, and a professor at UW-Madison, J.R. Schmidt. And so we're using sort of a hometown product there. These are some of the sorts of images you're going to be used to seeing in the WebMO software, and we'll talk about those as we move forward. So as a general background to computational chemistry, essentially it's all based on our ability to predict the geometry of molecules. The level of theory and the basis set that are chosen are designed to give good geometries. We're not going to talk too much about the mechanics of how the calculations work in the scope of this course. You can trust that we've chosen reasonable ways to approach the computational chemistry so that you're going to get a reasonable geometry. And from that geometry, we're going to get all kinds of other useful information about physical properties of the molecules and the relative energies of the various structures. So the general motif is that the first thing you're going to do with any molecule is get a good structure, and then from that, the remainder of this list are things that we can find out based on that good geometry. So we're going to spend a lot of time in this particular lecture looking at the electronic structures of molecules, and by that I'm referring to the molecular and atomic orbitals that we're used to discussing in chemistry, and we're going to get some great images of those orbitals. We're going to look at bonding orbitals, we're going to look at lone pair orbitals, we're going to look at anti-bonding orbitals, and we're going to use those to understand the chemistry of molecules. We're going to, in part of this course, explain the regio and stereochemical outcome of an organic reaction based on some computational study that we're going to do. We're going to specifically take a look at some reactive intermediates in the pathway of these reactions and use that to understand the outcome. We're going to spend a lot of time talking about the stabilizing and destabilizing interactions of molecules. We're going to look at exactly the things you've already talked about in your previous courses, steric interactions or steric repulsions between parts of molecules. We're going to look at orbital overlaps, we're going to look at hydrogen bonds, and we're going to understand these at a deeper level through computational chemistry. Of particular use in organic chemistry is the ability to predict spectra based on computational results. In this course, we're going to predict a couple of NMR spectra of molecules. A few times that's going to be required as part of a post-lab question, but these are also available for you to use at any point to help predict an NMR spectra of a molecule you're trying to assign. It's a powerful and useful tool. We're going to be predicting the infrared or vibrational spectra of almost every molecule we look at, and I'm going to talk a little bit about how to use the IR spectrum in order to determine whether or not a calculation has succeeded or a calculation might not have given you the structure you're hoping for. We're not going to use the other ones too much in this course, but certainly other spectra can be predicted. We're going to focus on the infrared and the NMR. Of particular excitement for me is the ability of computational chemistry to predict transition states. These are species that exist at the top of a potential energy surface. They're not stable structures, And as a result, they have incredibly short lifetimes on the scale of 1 molecular vibration. And a species that's that short-lived can't traditionally be studied by any of our traditional spectroscopies. And so computational chemistry offers us a really good way to get insight into these transition state structures for chemical reactions. And so this is sort of a general background of the types of things we're going to talk about this semester and the types of things we're going to do in Chem 344. So in order to make that sort of leap from thinking about molecules using molecular modeling to relating them to the experiment, we need a little bit more background information. And so I want to build up kind of slowly our understanding of molecular orbital theory, how it connects to resonance structures, and how it connects to sort of formal charge. And so I want to start really simply and look at the H2 or hydrogen molecule. This is a structure that's present in just about every textbook that includes molecular orbitals, and so it should be some good review. The hydrogen atom has an electron in the 1s orbital. When you bring 2 of those hydrogen atoms together, you get a hydrogen molecule. And when those orbitals overlap, they do so in a pretty predictable fashion. You can either add the wave functions together, which results in this bonding orbital where we have good overlap between the 2 hydrogen atoms. You can see it has a red color. WebMO will make any filled orbital red or blue color, and any empty orbital, like this one, will show up in yellow and green. The 2 electrons from the 1s orbitals on the hydrogen atoms come together and are in the bonding or the HOMO orbital here shown in red. The LUMO orbital up here is yellow, green, and empty. The name HOMO and the name LUMO actually tell you where the electrons are in that molecule, and I'll define those further in a second. The bonding orbital down here is a stabilized orbital. There's a benefit in terms of the energy of the molecule relative to 2 unpaired sigma orbitals. The LUMO orbital is destabilized or higher in energy relative to that sort of center point. As I said, these are generated by 2 1s orbitals overlapping to make a sigma molecular orbital. A sigma molecular orbital has its electron density along the bonding axis. As we go higher in energy, we introduce nodes into the orbitals. This bottom orbital has a complete overlap from one s orbital to the other s orbital. The higher energy orbital has a separation where we know a place where there isn't electron density. And the general pattern holds true that as you go up in energy, you go up in the number of nodes in a system. So, as you've learned in the past, generally the lowest energy orbitals are occupied first in ground state molecules, and so 2 electrons here are in the lower energy orbital, which is the highest energy occupied molecular orbital. It's a bonding orbital. There are no electrons in the LUMO, or the lowest unoccupied molecular orbital. And as I said previously, WebMO nicely colored these orbitals in a red-blue fashion for occupied or yellow-green for unoccupied. The most important thing to take away from this slide is the symmetry of sigma-type orbitals. This is something that often causes people confusion when they're looking at orbitals in a molecular orbital output or a natural bond orbital output from a WebMO-based calculation. These sigma-type molecular orbitals all have their electron density around this axis, which I highlighted in blue here, and it is radially symmetric around that axis. And this is sort of a typical single bond where you see a sharing directly between those 2 nuclei, and this region has the electron density. And we're going to contrast that in a minute with pi bonds. But this idea is quite important to keep in mind. So if we move up in complexity slightly, we can move from the hydrogen molecule to ethane. Ethane is C2H6. It has a number of sigma bonds in the molecule. I'm going to focus on this slide to the carbon-carbon sigma bond, and we're just going to look at the sigma bond that's created between those 2 carbon atoms. We could apply the exact same sort of analysis to all of the CH bonds, but we're just going to focus on that part for simplicity's sake. before, if we bring those two atoms together and form a bond between them, we're using two atomic hybrid orbitals, one for each carbon atom. As we overlap those orbitals, we make two molecular orbitals. One, the red blue down here is occupied, and is a sigma bonding orbital. One up here is yellow-green, and unoccupied is our sigma star orbital. The highest energy one of electrons is this one, so it's labeled HOMO. The lowest energy orbital that's unoccupied is this one, it's labeled LUMO. And again, the bonding orbital is stabilizing or lowering energy. The anti-bonding orbital, the one with the increased number of nodes, is destabilizing and higher in energy. And just like with the H2 example, these are sigma bonds, so they are radially symmetric in shape about the bonding axis, which I've highlighted in blue here. These are a little bit more complicated than just overlapping the s orbitals we saw in the hydrogen molecule. Here we have some little blue pieces out of the end and a red piece in the center, so there's a phase change there and some nodes involved. And that comes about because these orbitals are made of two sp3 atomic hybrid orbitals rather than these sigma bonds being created by two s orbitals. So here are images of those two sp3 atomic hybrid orbitals on each of the carbon atoms. This is the sp3 orbital on the left atom. This is the sp3 hybridized atomic orbital on the right atom. When those two orbitals come together and form a bonding orbital, it becomes this one. When they're brought together and the wave functions are subtracted, that forms this anti-bonding unoccupied LUMO orbital here. As with before, the higher energy orbital has an increased number of nodes, and so the lower energy orbital here has one node on each end, separating those red and blue parts. And as we go up in energy, we introduce a new node into the center, separating the orbital on the right and the orbital on the left, and essentially create a region where we don't have good overlap between the orbitals of those atoms. That's what makes this an anti-bonding orbital. So the same terminology applies. HOMO is the highest occupied molecular orbital, LUMO is the lowest unoccupied molecular orbital. Those are terms you're going to hear quite a bit. And in many cases, especially when we're talking about pi systems, the HOMO and the LUMO are important to understand the chemistry of the molecule. They're important to understand the UV-Vis spectrum of the molecule, and they're critically important for all the very cyclic reactions that are discussed in Chem 345. And again, as I said at the beginning, we could have performed the same sort of analysis with all the CH bonds as we just did with the CC sigma bond. So let's contrast those sigma orbitals with some pi-type molecular orbitals. And again, I want to start with a very, very simple case. This is the case where we have ethylene. We have a sigma bond that exists between the two carbons, and we add an additional bond, a pi bond between those two atoms. I'm not going to show the sigma bond orbitals, but they're still there, just like in ethane, and they're much the same shape and description. But we're going to instead focus on the pi system here, which is that second bond. So some important contrast and similarities will be obvious, I think. The first is when we increase the energy, we go up in the number of nodes, just like last time. So in this bottom orbital, we have great overlap above and below the plane of the molecule from one carbon to the other. When we go up in energy, we increase the number of nodes, so we have a separation between those two orbitals. The electrons in the ground state are in the highest occupied molecular orbital, which is the lower energy one here. The empty orbital is at pi star, the LUMO orbital there. The shape and symmetry of these molecules is in orbitals is a little bit different than the sigma type. These have a nodal plane running through all the nuclei in the molecule, and the sigma bonding axis is sitting directly in that nodal plane. And so even in the completely bonding orbital, we see that there is a node which is separated into two lobes above and below the plane. And that node shows up in both the HOMO and the LUMO. The difference here is that this is formed by two p orbitals, and the p orbitals themselves are symmetric above and below the plane, and have a nodal plane at the nucleus of the molecule, nucleus of the atom. And so we bring those two p orbitals together, that nodal plane still exists, which is why it shows up in the body orbital. The presence of this p orbital in each of those atoms implies that we have an sp2 hybridized carbon atom, which is what we would expect for a molecule that has a carbon making a single double bond. It has a trigonal planar shape around that carbon, and it has one p orbital left over that it can use to make that pi bond. The carbon-carbon sigma bond, carbon-hydrogen sigma bond, those are used by some roughly sp2 atomic carbon orbitals to form those bonds. If we make our system slightly more complicated, we can add a second pi bond. This is being understood in almost exactly the same way as our ethylene molecule on the previous slide. This is acetylene, or C2H2. There are now two pi bonds in this molecule, but the exact same ideas are going to hold true. There is, again, a nodal plane separating the two lobes of the pi bond. And again, the molecular axis runs right through that nodal plane. There are 4 electrons shared in these two pi bonds. And so 2 of those electrons are right here in this pi bond, the other 2 electrons are right there in that pi bond. And if you notice, they are perpendicular in their orientation. This one has its density mostly up and down in the plane of the swinging. And this one has its electron density sort of aimed away and coming out at us in the orientation of the screen. They result from some orthogonal or perpendicular p orbitals, which we'll talk about in a second. As we go up in energy from these two equal energy or degenerate pi bonds, we get these pi star orbitals that are themselves degenerate or equal in energy. And they are unoccupied, so we label them with pi star. WebMO is depicting them in yellow-green to show they're not occupied. And we go from no nodes in our pi bonding orbital to one node in each of our pi anti-bonding orbitals. Those pi bonds and pi star bonds are formed from a set of p orbitals at each carbon atom, where one p orbital is in this orientation and can overlap to make this bond. The other set of p orbitals are perpendicular to those, and they can overlap to make that pi bond. Because the p orbitals themselves are equal energy at the carbon atom, we get 2 essentially equal energy or degenerate pi bonds created. And the presence of both of the p orbitals at each carbon atom implies these are sp hybridized carbon atoms, which is what we expect for a molecule such as acetylene, where we have 2 pi bonds connecting the carbons, and each carbon is making an additional sigma bond to the carbon and to the hydrogen attached to it. So now I want to step up the complexity one bit further, and instead of showing a pi system as an overlap of 2 adjacent atoms, I want to extend that to 3 atoms. And you're going to see some patterns here that are going to hold true regardless of the size of the system. And one of the key issues is how many orbitals are involved in that conjugated pi system. And that's an important thing to pick up on this slide. I've got the resonance structures of allo-cation, or C3H5 also picked up here. And note that these are a really simple way to depict pi conjugation. I really want to stress that resonance structures are not real. They're not based on any physical reality, but there are pictures that allow us in a quick and simple fashion to depict pi conjugation. The convention of resonance structures is that neither the structure on the left nor the one on the right is the actual depiction of the allo-cation, but this resonance area tells us that somewhere in between these 2 structures is where the molecule really exists. We're going to use computational chemistry compartments on the left. In the process of optimizing the structure, the computational software realized that each of those bonds are equivalent. It doesn't change the depiction in the output of a double bond and a single bond, but the bonding distance is exactly the same on each side of that molecule, sort of indicating the same thing we would assume when we see these resonance structures. That there really is about a bonding order of 1.5 between each of those carbon atoms. And so the computational software figures that out by optimizing the structure. We sort of figure that out by, in our mind, finding an average between those two resonance structures based on how useful they are to the overall structure of the molecule. I then performed that second calculation I mentioned, which is the one that gets us these orbitals. You're going to do quite a bit of these NBO calculations to display the orbitals of a molecule. And when I did that, I found these three p-type orbitals located at each of the carbon atoms. And you can tell that they're p orbitals again because we have symmetric lobes above and below the plane of the molecule. And we see one of these at each of the carbon atoms, which isn't surprising because in order to have a pi system, we need orbitals that can overlap well. And these p orbitals do just that. The key idea I mentioned a few minutes ago is that we need to pay attention to how many orbitals are created in our manifold of molecular orbitals. And the statement that is true for all of these cases is that the number of molecular orbitals produced is equal to the number of atomic orbitals that are overlapped together. In the case of H2 or ethane, we look at bringing two orbitals together, which made two molecular orbitals. In this case, the alkyne, we're going to bring together three orbitals, which should make three molecular orbitals. And here they are. We now have three of them because they're based on our three p orbitals from each of the carbon atoms. The lowest energy orbital shows great overlap from one end of the molecule to the other, which is what we would have expected thinking about these resonance structures. We see that we have a double bond on the left, single bond with a cation on the right, and then another resonance form, we have a cation on the left, and a double bond on the right, and that indicates to us that there's some sort of delocalized pi system involving all of those carbon atoms, and that's exactly what we see when we do a more sophisticated approach and look at the bonding orbitals. This one is red-blue, which tells us it's occupied. Both of these are yellow-green, which tells us they are unoccupied. Again, there's a nodal plane running through the middle of the molecules. I've added this dashed line to indicate the energy of three non-bonded p orbitals, and that's sort of our 0 point. This energy is much more stable than sort of three isolated p orbitals. This orbital is destabilized, and so we don't change the total energy. The total energy of our orbitals is always going to remain the same, and with three orbitals, that naturally means one of them has to get no energy change. The reason the alkyne is so stable is because the electrons exist in this low energy orbital that doesn't have any nodes. It has great bonding overlap across all of those carbon atoms. So again, we have two electrons in the system, which we can see back from our resonance structures. Those two electrons go into the lowest energy orbital. That is the orbital labeled down here as pi1. It is also the HOMO, or highest occupied molecular orbital, because that's where the electrons are. One higher in energy than that is the LUMO. One higher in energy than that is the LUMO plus 1. And if we were talking about an orbital beyond that, we get the LUMO plus 2, the LUMO plus 3, and so on. And if we're discussing the orbital lower in energy than the HOMO, that's the HOMO minus 1, the HOMO minus 2, and so on in the other direction. It's often convenient with these organic pi systems to label one of them pi1, pi2, and pi3, and simply count them that way. You're going to see both of those notations. This superscript here at NB means it's a non-bonding orbital, which simply just means that its energy is neither higher nor lower, neither destabilized or stabilized. This star up here indicates that that's a higher energy destabilized orbital. So that's the alkyne. We have three atomic orbitals in the system, which resulted in three molecular orbitals. And on Unsurprisingly, all of these carbon atoms are sp2 hybrids. They are all trigonal planar, and they all have one of those p orbitals that are used in that pi system. So let's extend that system a little bit further, and again look at some sp2 hybridized carbon atoms. In this case, we're going to look at butadiene, which now has 4 carbon atoms in the pi system. We can draw this series of resonance structures, which is in every textbook showing this orbital overlap. And in chapter 14 above, we learned that the double bonds on the ends of the molecule are actually a little bit longer than you expect for a double bond. The single bond in the center is a little bit shorter than you would expect for a single bond. And we can justify that by looking at these resonance structures, where we see that there's some pi bonding character between the two central particles. Or we can use molecular orbital theory and take a look at those orbitals directly. So I've optimized the structure of the molecule over here. That's the geometry of butadiene. And then I've done a secondary or NDO calculation. This gives us a set of molecular orbitals. And just like before, with 4 atomic orbitals coming in, we get 4 molecular orbitals out. 2 of which are stabilizing relative to the center point, 2 of which are destabilizing. There are 2 pi electrons coming in from each of those bonds for a total of 4 electrons. The 4 electrons go to the lowest energy orbitals, pi 1 and pi 2. We label the highest occupied molecular orbital the home, 1 more energy that is the whole minus 1. And all of the same trends we saw in the previous slides hold true here as well. We have high symmetry orbitals because they're made from p orbitals. Here's a depiction of the p orbital at each of the carbon atoms. 4 of these p orbitals come together to make 4 pi molecular orbitals. As we go up in energy, we increase the number of nodes from no nodes at the bottom to 1 to 2 to 3. And so we see an increase in energy as we increase the number of nodes. And this gives us a much better and more realistic depiction of the pi system of this molecule than we can get from resonance structures alone. The reason is stabilizing to have 2 double bonds adjacent to each other in a molecule separated by a single bond is because these 2 orbitals are generated and they are filled with electrons. And these are stabilizing orbitals, and much more so for the whole minus 1 than the whole, but both of these are low energy, good orbitals for the electrons to reside in. So if we take that one step further, I'd like to finish our molecular orbital examples with benzene, which is now a cyclic system. There are a few changes here, but for the most part, things are very, very similar to what we've seen in the other systems. We now have 6 atoms in conjugation. So 6 atoms, each contributing a p orbital, results in 6 pi molecular orbitals. So that's exactly the same as we've seen before. The difference is that pi 2 and pi 3 happen to be the same energy. Some textbooks use frost circles at this point to give you a way to predict the energies of all 6 of the orbitals, particularly pi 2 and pi 3 being degenerate or the same energy. That's not something that we're going to worry too much about in this course. We're actually going to do some calculations in chapter 5 where you're going to look at some aromatic pi systems and you're going to find these orbitals for yourself. You're going to start with benzene just like this and then work on some substituted benzene. You should be able to find the pi symmetry orbitals by their shape. We've got nice symmetrical lobes above and below the plane. And you can find their occupancies and their energies in WebMO, and I'll talk more about how to do that on a later slide. For right now, we see that as we go from 0 nodes in the pi system, we still have that node in the plane of the molecule, but a completely bonded pi 1. So we go up in energy and increase the number of nodes. We get 1 node in pi 3 increased number of nodes are a degenerate pair or an equal energy pair of pi 4 and pi 5. Both of these are labeled with a star because they are unoccupied high energy orbitals. There's one node here, a perpendicular node right there, one node right here, and a perpendicular node right there. So each of these has 2 nodes. The highest energy orbital is pi 6. It has 3 nodes, sort of bisecting the molecule, and as a result has completely separated most of those orbitals. And one of the most important things you want to see visually when you're looking at these is that the lowest energy orbital, pi 1, will always have complete overlap around the ring and will have no nodes in the pi system. That's always going to be true for the lowest energy orbital. The highest energy one in the system is always going to have complete separation as you go around the ring. And so those p orbitals are essentially isolated. That's the high energy orbital. And you can sort of use those two as bookends when you're looking at a pi system. And one of the things that people struggle with a little bit early on when looking at these aromatic pi systems is knowing how many orbitals they should be looking for or where they are in the molecular orbital list. Well, the number is easy. The number of atoms in conjugation here is 6. That's equal to the number of orbitals that are involved in the pi system. And the pi orbitals are usually near the homo-LUMO gap. If you start at that homo-LUMO gap, you can work down until you find one with complete overlap. And you can work up in energy until you find one with complete separation. And that sort of indicates to you that you found all the necessary pi symmetry orbitals for a particular system. And again, the big conclusion here is the stability of benzene is based on the occupation of these orbitals. Everyone remembers the Hubble rule of 4n plus 2 pi electrons, meaning a molecule is likely to be aromatic if it's a cyclic conjugated system. Well, the reason that works is because these are the orbitals that are occupied in those cases and in those molecules, and this is what gives rise to that aromatic stability. Okay, so that was a lot about molecular orbitals. I want to switch topics a little bit and talk about some formal charges and how we can think about the electron distribution within a molecule in the context of computational chemistry. So we are going to do the exact same sort of thing in that I'm going to show you on 2 molecules where I've optimized the structure. So step 1 is always get a good geometry. Step 2 is perform a second calculation. In this case, I run NBO calculations to get these NPA charges, or natural population analysis charges. NBO and NPA are good ways to look at these things. So I started out with a water molecule here. And as the water molecule is optimized, we're able to get a dipole moment directly based on the charge distribution. And not surprisingly, we find that water has a polar structure where we have a negative end by the oxygen and a positive end by these hydrogens and a dipole moment in this direction. We can show that in a slightly prettier way. This is an electrostatic potential map where we see a pretty color gradient going from the blue, more positive hydrogens, to the red, more negative oxygen. And you've certainly seen images like this in your textbooks. These are sort of a pretty way to show the same information that can be shown with this dipole moment arrow over here. But what usually is more useful for predicting reactivity and thinking about how molecules are likely to behave is actually looking at the NPA, or natural population analysis charges at each individual atom, which we can also get out of an NBO calculation using WebMO. And these are the ones that we're going to use throughout the semester to think about reactivity and think about these structures. There's a couple of conventions. WebMO will display all the negative charges in red, all the positive charges in blue. It puts the charge in tiny little white letters and numbers right on the red and blue spheres. The size of those spheres is related to the magnitude of the charge. I've rewritten them there so they're actually visible, but we have a large negative charge on the oxygen, almost a full electron's worth of charge. We have a smaller positive charge on each of the hydrogen atoms, half that size. itself. And the important thing to remember here is that oxygen has an electronegativity about 3.5 on the Pauling scale. Hydrogen has an electronegativity about 2.1 on the Pauling scale. And when you bond them together, the oxygen will always draw electron density away from that hydrogen atom, which is going to be important for my next slide here. So, you're used to thinking about drawing resonance structures to depict the charges in molecules, and I want to take a moment to clean up what I think is a common misconception that people have about charge in molecules that results in their use of resonance structures, and in particular from the formal charges that result in those resonance structures. This is an example of benzoyl nitride, which has a cyano group attached to a benzene ring. Cyano groups are electron withdrawing, and you can see that the resonance structures that can be drawn for a cyano substituent include the formation of this carbon-carbon double bond, indicating that there's some carbon-carbon pi bonding character existing between these two atoms. You see that the electron density is moved out to the nitrogen atom in those three resonance structures, leaving an efficient carbon at three locations around that ring. Now, none of these are the actual picture of the molecule. The molecule exists as some weighted average of these structures, but the impact of these three resonance structures over here is that almost certainly we have the ortho and para positions on that aromatic ring with a little bit of electron deficiency. Now, if you forget that these resonance structures are just single snapshots of the molecule and you have to put them all together to get the true structure, or you forget that formal charges are just bookkeeping tools, it's really easy to think that these carbon atoms actually have a positive charge. What we do want to take away from these resonance structures is that there is a delta plus, or a change in the charge in a positive direction at the ortho positions and at the para position relative to that cyano group, and that's going to occur whenever we have an electron withdrawing group attached to an aromatic ring. What isn't true is that those carbon atoms are actually positive. All of the carbon atoms that are part of that aromatic ring have a negative charge when we look at the NPA charges. And that occurs because those carbons are bound to less electronegative hydrogens. And the charge on carbon atoms attached to hydrogens is generally going to be negative. In this case, it's not the same at each carbon position because of the substitution. Relative to benzene, they've all been changed a little bit. Benzene at this level, theory and basis set, has a charge at the carbon atom estimated at minus 0.24. What we can see here is that the ortho positions, that charge is less negative. Less negative is another way of saying more positive. And so you see that the effect of the cyano electron withdrawing is enough to perturb the charges a little bit of those ortho positions, make them less negative. The para position, likewise, is also less negative. But interestingly, the resonance structures here don't predict which carbon is actually the most positive. The most positive, or least negative carbon, is the ipso one here, where the cyano group is directly attached. It turns out the sigma electron withdrawing effect of that cyano group is more substantial than the pi electron withdrawing effect that you see around the carbons of the ring. And the only carbon in this molecule that's actually positive is the carbon of the cyano group itself. It has 3 bonds to nitrogen. Nitrogen is a more electronegative element, and it's drawing electron density off of that carbon atom. The important take-home message here is that resonance structures and formal charges that result from those resonance structures don't actually predict the charge on the atom. What they do predict is the relative charge change. And so you can expect when a cyano group is attached to an aromatic ring that as the resonance structures would predict, the charges change in that direction. But we can see here that those carbons stay negative regardless of the substitution.
So let's focus a little bit more on formal charges directly. And this is an area where I think almost all students coming out of high school chemistry, coming out of general chemistry, and coming into organic have some significant misconceptions. And this is something that chemists, even years later, after they've had organic and they've had CHEM, still struggle with. And it's because of how we treat formal charge and how we talk about it in many ways. And I'd like to use hydronium as an example to discuss this misconception. Hydronium is a Lewis structure you've probably drawn hundreds of times. It's water with an extra H plus attached to it, so it's an H3O plus. Now the problem comes in after you've drawn this molecule hundreds, possibly thousands of times. It's really easy to forget what you were told about that plus charge on the oxygen when you first started drawing these structures back in high school. You learned that formal charges were a way to keep track of electrons, and they were essentially a bookkeeping tool that allows us to pay attention to where the electrons are in the molecule after bonding. And in a formal sense, that oxygen does have a positive charge. The problem comes in after drawing that structure many times, you start to believe that the oxygen is actually positive, which is absurd when we think about the electronegativities of these atoms. Oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. There's a huge difference between those two atoms. These bonds are very polar, with electrons moving towards the oxygen. Believing that oxygen is positive is in direct conflict with that. And when we optimize the structure and run a charge calculation, we see exactly what we just talked about. The oxygen is the one that's negative. Each of the hydrogens bears a positive charge. The formal charge is exactly wrong here. It creates a plus charge on the oxygen. That oxygen has almost a full negative charge. Formal charges often are wrong because, in terms of real charge, because they ignore factors from electronegativity. We can do an electrostatic potential map here and see that pretty image again, where we got the negative end by the oxygen, the positive by the hydrogens. And the important thing here is that these charges are much closer to the real charges of the molecule. These are computational estimates, but they match the reactivity. Hydronium is an acid. It's an H plus donor. It's a molecule that's good at giving away H pluses, which doesn't make a lot of sense if we think about the oxygen bearing that positive charge. Here's another example where formal charge doesn't do such a good job of representing the real charge. This is the tetrafluoroborate anion, where we have 3 fluorine atoms attached to a central boron. In order for boron to be tetravalent like this, it has to have a negative formal charge. It has 3 valence electrons. Here it has an extra bond, which gives it a negative formal charge. When we look at the optimized structure and the NPA estimated charges, that boron is about 1.5 positive charge units. That's the charge on an electron. It's got about 1.5 plus charges, as opposed to the negative formal charge there. So again, electronegativity is important. Fluorines have an electronegativity of about 4, boron right around 2, so that is an incredibly polar bond. And as a result, we see that the boron bears the positive charge and the fluoride the negative charge. So the important thing is, as you're thinking about organic chemistry or organic reactivity, is that you recognize that formal charges are not representing real charge, and to the extent that you actually believe formal charges are real, a lot of organic chemistry reactions don't make sense. Now I want to finish part 1 here by looking at 2 examples where believing formal charge to be real makes the chemistry really confusing. So the first example comes out of an EAS, or electrophilic aromatic substitution reaction. This is one that is run in Chem 344 every semester. This is a nitration reaction. And the first part of the nitration reaction is generating this NO2 plus cation. That is the extreme electrophile that's generated in the EAS reaction. That's the species that does the reaction with the aromatic system. And so the first part of the reaction is making the NO2 plus, and it's made by reacting concentrated nitric with concentrated sulfuric acids. This is a neat reaction where the stronger sulfuric acid protonates the slightly less strong nitric acid. Now, nitric acid exists as a combination of these two resonance structures, where we have a negative formal charge on one oxygen, double bond to the other, or in an equivalent structure, we can show a negative formal charge on one oxygen and a double bond to the other. This structure gets protonated by the stronger sulfuric acid in the first step of the reaction. We know this happens because we know that water is generated and an NO2 plus is created. That's observed experimentally. And this is the mechanism by which that happens. The oxygen with the H already attached to it has two lone pairs, picks up a hydrogen to form this intermediate. That intermediate then decomposes by the breaking of that NO bond to make an NO2 plus and a water leaving group. This reaction doesn't make a whole lot of sense if you believe the formal charges over here. If you think that the oxygens with the negative formal charges are the most negative oxygens in that molecule, then they would have to be the most basic. They would have to be the ones that would be most able to pick up that hydrogen atom. It turns out the formally negative oxygens right here are not the most negative oxygens in that molecule. If you optimize the structure, it looks like this. A quick NPO calculation reveals these charges. And we see from them that these two oxygens have about minus 0.3 charge. The oxygen that already has the hydrogen is significantly more negative, with a charge of minus 0.5 here. The reason it's more negative is because it's attached to a hydrogen already. The hydrogen is positive, the oxygen is negative. It is then more basic or more able to pick up the extra hydrogen from the sulfuric acid. Conveniently, this forms a water leaving group that can then leave and make the NO2 plus cation. A second example, also from EAS, about where formal charges don't work so well, if you believe they're real charges, is one that actually bothered me quite a bit as a student. When I was a sophomore taking organic, this is a reaction that made no sense to me. And looking back, I know why it made no sense. It didn't make sense to me because I actually believe that the oxygen in the species had a positive charge. Well, that's a little bit silly now when you've been thinking about electronegativity. An oxygen, which is a highly electronegative atom attached to a carbon, it's going to be drawing all kinds of electron density off of that carbon atom. So that plus formal charge of the oxygen can't really be the actual charge on the oxygen. And a quick calculation reveals that. A quick optimization gets this structure for a psyllium. We see from an NPO calculation that the oxygen in the center here is much more positive. It has almost a full positive charge on it. I'm going to back up and redo that slide.
Just stop a minute.
Okay.
Okay. Okay. We're ready. Stop this. A couple comments.
Okay, so this is an example right out of the 344 curriculum. This is from an EAS reaction, which is electrophilic aromatic substitution. And it involves nitration, which you'll be doing toward the middle part of the semester. In order for a nitration of an aromatic ring to occur, an NO2 plus cation, this species, needs to be generated. This is an extreme electrophile and it's reactive enough that it can react with an aromatic system. The interesting part, and the part that relates to the misconception of formal charge, is the generation of that NO2 plus cation. It's generated by a reaction of nitric acid with sulfuric acid. Nitric acid has a pKa of about minus 1.7. Sulfuric acid has a much more negative than minus 3 pKa. So the stronger acid, sulfuric acid, protonates the nitric acid, and in a two-step process, we produce a water leaving group, an NO2 plus cation, and a hydrogen sulfate counter anion. The formal charge misconception comes in how the reaction actually occurs and what the reaction mechanism is. So on the left here, I have the structure of nitric acid. The two most important resonance forms are depicted. We've got a negative formal charge on an oxygen, double bond to the other one, a negative formal charge on that other oxygen, and a double bond to the one that was previously drawn with a negative formal charge. So the formal charge tells us that each of these oxygens share, by these resonance structures, about half of a negative charge each, for a total shared minus 1 charge. The stronger acid, sulfuric acid, protonates the nitric acid, and then the reaction occurs. The mechanism is known. This is it. The first thing that happens is the hydrogen atom is attached to one of those oxygen lone pairs. The OH bond of the acid is broken. This produces a really nice water leaving group, which leads to the water that's observed in the reaction. This species, as reactive intermediate decomposes, produces a water leaving group and our exciting NO2 plus cation. The interesting part is why this is the oxygen that picks up the H plus and not these other oxygens. And this is where the formal charge issue comes in. If we believe formal charge, we believe that these are the two oxygens that are negative, it doesn't make sense that the other oxygen is the one that picks up the hydrogen atom on the nitric acid. A quick calculation using Gaussian 09 through WebMO gives us a structure that looks like this. A very simple NBO calculation will help us predict those charges. And we see that the formal charge is wrong in terms of its depiction of the real charge. Both of the formally negative oxygens that share that minus half a charge actually have real charges much closer to minus 0.3. The oxygen without any negative formal charge has a charge of about minus a half. This is the most negative oxygen in the molecule, and as a result, it is the most basic of the oxygen atoms in the nitric acid molecule. It's the one that is most able to pick up that hydrogen, which is convenient because that's what forms the water leaving group, which then can decompose to make the NO2 plus cation. You're going to do this reaction later in the semester, and this is a decomposition of a protonated nitric acid that you're going to need to be familiar with. And we can rationalize it much better by thinking about the NBO charges rather than the formal charges of the nitric acid. The second example I have here is also from an EAS reaction, and this is one that I remember being baffled by as a student when I was a sophomore taking organic chemistry. And it comes in because I believe that this oxygen actually had a positive charge to it because I internalized formal charge and I believed it. And I didn't understand why the aromatic ring reacted with the carbon atom. I mean, the ring is donating electrons are negative. I didn't understand why they weren't being donated to the positive oxygen, but they were being donated to the carbon atom. I assumed that the oxygen atom would be most electrophilic because it had that positive charge. And I made that assumption because I believed that formal charges were real. A very quick and easy calculation on this acylium cation produces a geometry that looks like this. The carbon atom at the center has a plus 0.97 charge to it. The carbon bears the positive charge here. The oxygen atom has about a minus 0.2 charge, which is the opposite charge that's listed up there with the formal charge. So clearly by these NPA charges from NPO calculation, the carbon atom is the most positive and should be the most electrophilic. And so again, we want to emphasize that this idea of formal charge being useful to predict reactivity is a little bit tenuous. It is very good for bookkeeping and counting of electrons, NBO charges do a much nicer job actually predicting the reactivity of these species and identifying which atom in the nitric acid is most basic and which atom in the Esselman is the most electrophilic. So this sort of ends part one, and in part two we're going to move into actually going through the process of generating these species. We're going to go through the same steps that I did to generate the ones from this part of the presentation. We're going to draw molecules in WebMO. We're going to get good geometries for them, and then we're going to do the secondary sort of NBO calculations that have been done here to generate this data.